Alrighty.
I'm surprised.
Good morning. Good morning, everybody. Welcome back to Calc 1. Plan for today is I have a quiz for you as promised on Standard 14, and then we're going to jump into Standard 15, start talking about properties of the first derivative. Specifically, what does it tell us about how we can graph functions? As far as office hours go, I've got office hours today and Wednesday from at 11 and 2, and tomorrow at 11 and 1. And as far as homework goes, you've got an exam on Friday. Don't forget, over standards 1 through 14. A few of you emailed me over the weekend to let me know that WebWork is acting up. I could not get into WebWork. I tried resetting the WebWork server. It has not helped. So I'm gonna have to contact the people who are managing the service for us and tell them, hey, this ain't working. What the heck? And hopefully they'll get that fixed soon. Anyways, long story short, I know you can't get in to actually do your WebWork homework, and so all homework is currently postponed. So don't worry about trying to do homework before the due date. Once I get this WebWork thing figured out, I'll contact the class and push back deadlines as appropriate to give you all, make sure you all have at least a couple days to work on those homework assignments. Thank you to those who contacted me over the weekend to let me know about that. The website that we use to manage the WebWork server is a real pain. Any questions or comments before we get started for today? So, yes?
So, Standard 15 won't be on the exam then?
Depends if we finish it on Wednesday or not. Okay. If we finish it by Wednesday, I'll go ahead and put a Standard 15 question on there. Standard 15 is a little bit long, so I'm not sure if we're going to finish it Wednesday or if we'll have to go into next Monday to get that one 100% complete. We'll let you know at the end of class Wednesday. Yes?
Will this be like the last exam?
Yes, it will be exactly like the last exam, except twice as long. So, as I said before, I recommend for this exam you don't go in trying to do every single standard on the exam, because I haven't written it so that you go through it with the intention that you go through every question. Instead, I recommend that you pick out maybe 6 or so standards that you feel like you're ready for, the ones that you want to focus on for this exam, and just do those questions. Better to make sure you have enough time to do all the questions you want, rather than trying to rush through everything and probably get very few masteries in the process. Yeah, format's the same. You can bring in one sheet of notes front and back, just like with the last exam. Yeah. Other questions or comments? If anybody wants to come talk to the exam about the exam with me this week in office hours, I'd be happy to talk with you and maybe give you some test taking tips if you would like. Okay, so one day Rene Descartes walks into a bar, goes up to the bartender, asks for a drink, gets a drink, nurses it down. Bartender asks Descartes, "Would you like another?" And Descartes thinks about it for a second and says, I think not. And then vanishes into thin air. Because now he is not. Okay, next, go ahead and put everything away. It is quiz time.
Did you enjoy your DQs?
I do.
It was the chicken dinners were fast.
Quiz is out, so quiet in the room, please. I'm gonna draw a graph and start writing some stuff down on the board. It has nothing to do with the quiz and everything to do with the upcoming new standard, so don't worry about it. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Okie dokie. So, the next three standards all are going to share kind of a common theme, and that they're all going to be focused on the idea of finding maxima and minima. In other words, finding points where a function is kind of reaching its peak, is at the highest point it could possibly reach, and finding points where it's at the lowest it can possibly be. And standard 14 is going to be focused on how can we use the first derivative, f prime of x, to help us find where does f of x have sort of a high point and a low point to it. And standard 16, the next one, is going to be focused on how can we do the same sorts of things using f double prime of x, using properties of the second derivative. And then finally, standard 17 is going to be how do we sort of solve real-world problems, in other words, sort of doing word problems involving optimization. If we have, I've got an example planned out where we're going to be, pretend like we're working at the Coca-Cola Corporation and we want to design the perfect can to hold as much Coke as possible while being as cheap as we can. How can we do that in order to maximize our profits? Answering those sorts of questions. Exciting stuff. So to start with, I'm going to give you all a bevy of definitions to work with, and then I'm going to set you all loose working on an example. So we've seen the terms increasing and decreasing before, where increasing just means that as x gets bigger, meaning as x moves to the right, our f of x values become more positive. In other words, for an function that's increasing over some interval, we would say that as we move to the right on our graph, our y values are getting bigger, going upwards. Whereas if our function's decreasing, that just means as we move to the right on our graph, as x gets larger, our f of x values are becoming more negative. And throughout the next few standards, we're going to distinguish between two different types of maxima and minima for our function. We're going to talk about functions that have a local max and a local min, where we have a local max at a point if our y values are at that point are bigger than all the y values a little bit to the left and a little bit to the right of that point. And then similar for local min, y values at a point are smaller than all the y values a little bit to the left and a little bit to the right. And finally, we're going to distinguish that from absolute max and absolute min, where a function has an absolute max at a point if the y value at that point is the biggest it'll ever be across the entire graph. And similarly, our function will have an absolute minimum at a point if the y value is the smallest it'll ever be across that entire graph. And all these are kind of on the front page of the packet, but thought I'd briefly talk about it. All right, let's talk about how I screwed up on this packet. So if you turn to the second page of the packet, it asks you to consider the graph that is drawn below. I forgot to actually draw the graph before I made these on your version, before I made copies. So you're going to have to draw this graph in yourself, but this is what it looks like. And what I would like for you all to do, after you draw in your graphs, is to take a couple minutes and see if you can determine where is this function f of x from looking at the graph increasing versus decreasing? At what values of x does our function have a local max and or a local min? And finally, at what values of x does it look like this function has an absolute max or an absolute min? So go ahead and take a couple minutes and copy this graph down and then see if you can apply and find where are all of these things for this particular function. As always, you are welcome / encouraged to talk to your neighbors and to see if they agree with your thoughts on all of these. If you feel like you have answers for all of these, turn to one of your neighbors and make sure that they agree with you. Is the y value at that point less than all of the y values a little to the left and to the right? I don't think anywhere in the definition it explicitly says if it's one, it can't also be the other. Good question though.
I don't think that one's right.
Oh, okay.
What'd you got?
I think all of them with like the brackets and the U's. Right. Like the bracket and U's.
Can't learn anything if you don't try.
I think there's something. I remember there being a difference with like something. It includes it. Yeah.
Question about notation.
Brackets or parentheses.
Typically, if you have brackets, that means you want to include the endpoint, whereas a parenthesis you do not. Do not use a bracket if you have negative infinity or positive infinity on that side, because those are not numbers that you want to include.
I don't even get that type of discussion.
You want what?
The infinity thing,
What about it?
it's a number.
It is?
You can get there
You
eventually.
Eventually? How long does it take?
Dude, yeah, I know.
Couple weeks.
Yeah, and the thing is, like, what's after infinity?
Bigger infinities.
Exactly, that just gets me, oh my goodness.
We're actually about to talk about that in one of my upper level math classes. You can have different sizes of infinity.
It like makes no sense because like you can say like, oh, this goes to infinity, but this infinity is smaller than the infinity we have over there. Just
Typically, if we talk about functions going to infinity, it's just there's only one idea of infinity. When we talk about different sizes of infinity, usually we're thinking about different sets, and like we could talk about the infinity that's the size of all the counting numbers 1, 2, 3, 4, 5. The size of that set is smaller than the infinity that's the size of all the set of all real numbers, everything on the number line, for instance.
yeah, those are hugely different. Because there's infinite values from 1 to 2.
True.
I'm proud of
Would you believe me though if I told you that the size of this set, all numbers between 1 and 2, and the size of this set are the same?
No.
I thought they are.
There's no way.
But that's a different discussion. That's an office hour discussion if you want to have. Okay, it sounds like groups are starting to quiet down a little bit. So let's start off with the question of increasing and decreasing. Can anybody give me an interval over which it looks like this function is increasing? Josh?
-2 to +1.
From x equals -2 to x equals +1. Certainly looks to me like if we only are looking at values of x in this interval, that as we go from left to right in this interval, our y values are getting bigger. So yeah, I think that's a reasonable thing to say. So I'm going to say that it's increasing over the interval from -2, let's just say x between -2 and 1. And if you prefer, you could write this using sort of these open parentheses to say from -2 on the left to 1 on the right, over this interval, our function is increasing.
Why would you not use brackets? Because would you not include the numbers or?
Good question. Should we include the endpoints and say -2 less than or equal to x less than or equal to 1, which we could write using notation like this?
No, because at those points, the function isn't increasing or decreasing.
Yeah, I would typically say we're not going to include the endpoints. It technically wouldn't be wrong to for complicated reasons. So if you included the endpoints on a quiz or something, I wouldn't count it wrong. But typically, when you talk about increasing or decreasing, you usually don't include the endpoints of the interval you're looking at, for a reason we'll discuss here in a few minutes. But good question. Any other intervals over which this function appears to be increasing? Hannah?
If x is greater than 3.
Just x greater than 3? Yeah, if we look to the right of x equals 3 here, as we move from left to right, our function looks certainly like it's going to be getting larger, meaning the y values are going to be increasing. How can we write the interval x greater than 3 using this sort of interval notation?
3 to infinity.
Was that?
3 to infinity.
Yeah, we could write this using interval notation as being the interval from 3 stretching out to infinity. And here, if you tried to include, let's put a square bracket around infinity as an endpoint, that would be very much wrong. As Zach and I were just arguing, in this class we do not treat infinity as a number. In other math classes you can treat infinity as a number, with professor permission. How about where our function appears to be decreasing? When?
Negative infinity to -2.
from negative infinity to negative 2. I'm going to use this sort of notation from now on because it's a little bit more compact. But if you prefer using this way of writing out your intervals, that's also perfectly fine. So we could say from negative infinity to negative 2. Everyone all right with that?
Do you want to exclude negative 3?
I don't know, you're the one who answered the question. Do you want to exclude negative 3?
I don't know, I guess when I looked at it initially, it didn't look like it was horizontal. Slope of 0 at that point, but now I'm like second guessing myself. Okay, yeah.
This is why I need to have it drawn out in your packet ahead of time instead of you trying to read it off the board. And negative 3, it looks like our function flattens out briefly. I would say you could either treat this as just being decreasing from negative infinity to negative 3. You could include negative 3 or not in this case, since at negative 3 it flattens out for an instant, for a split second, and then immediately goes right back to decreasing. It doesn't start increasing or anything like that. So I would argue, technically, you could include negative 3 if you want, or you could split this up and say something like negative infinity to negative 3 and negative 3 to negative 2. I would say either way, depending on how you wanted to treat that, you could be considered to be correct. It's up to you though. If you want to treat like a single point where it flattens out before going immediately back to increasing or decreasing as being a point where you want to split up your interval or not. Any other intervals for which this function looks like it's decreasing? Rachel?
Between 1 and 3.
Yeah, we could also say between x equals 1 and x equals 3. Or, if you prefer, from 1 to 2, and then again from 2 to 3. Let's see, I think that cuts up the plane quite nicely. So, other than the endpoints of these intervals, everything's going to be in one of these intervals. How about values of x where this function looks like it has a local maximum? So in other words, is anyone able to find any values of x where the y value at that point is bigger than all the y values close by? Zach?
At x equals 1.
At x equals 1? Let's see. If we go a little bit to the right, looks like our y values are getting smaller. If we go a little bit to the left, it looks like our y values are also getting smaller. So yeah, I would agree that at x equals 1, it looks like we have a local max going on at that point. Any others? While we're on the subject, Zach, would you say that at x equals 1 we have an absolute maximum?
No, not absolute max, no.
Why not?
I mean, you have you have at 3 or 4, you have it going to infinity. And that function could go on forever, so. And it's already bigger than x equals 1, so that's probably going to be the absolute max at negative infinity and positive infinity.
Yeah, I would say already at x equals 4, we're getting y values that are bigger than what we would be getting at x equals 1. So while at x equals 1, the y values are bigger than what we get if we go a little to the left or a little to the right. If we go further to the left or right, past like x equals 4 to the right, past, I don't know, x equals negative 4 to the left, we're going to get larger y values. So I would say that at x equals 1, we have a point that's a local max, but not and absolute max. How about a local minimum? Are there any points on the values of x on the graph of our function where we would consider this function to have a local min, where the function is smaller than all the other, at that point, than all the other points close by? Colin?
X equals -2.
Ooh, at x equals -2. Everyone okay with calling that point a local minimum? You look like you're frowning at something.
I mean, I would probably say it's the absolute minimum because it's smaller than all the other points on the graph.
Ooh. Yeah, it looks like at this point, I would say that we have an absolute minimum. Because unlike at x equals 1, where it's bigger than the points close by, but if we zoom out far enough, we could get points with larger y values. I think at x equals -2, that's going to be the lowest y value no matter how far to the left or no matter how far to the right we would go. So to me, I would say this looks like an absolute min. Rachel?
Isn't it still technically also a local minimum?
You also think it can be both? Riley, what are your thoughts?
Yeah, I was just gonna say the same thing because it is still the minimum, like locally to the other points around it, even though it is still an absolute minimum.
Yeah, I think I would agree with both of you that even though it's an absolute minimum, I agree with Helen that I think we could also call it a local minimum because even though it's the smallest y value on the graph as a whole, it's also the smallest y value out of the nearby points as well. If you think of it like Jeff Bezos, richest guy on the planet. If we were to have a function that takes in a person and spits out their net worth, he would be an absolute. He would have an absolute maximum on that graph. If you also consider just, I don't know, people living in his neighborhood, he probably owns the whole neighborhood, but let's say just the city that he lives in, he's still the richest guy in the city, even though he's also the richest guy on the planet. And so you could still consider him to be have a local maximum for that function as well as an absolute max. There's nothing in the definition of local max that doesn't say that an absolute max couldn't also be a local max, and ditto with absolute min could also be a local min. Any other points where you have a local minimum? Or an absolute minimum, potentially? Let's see. Okay, Josh?
3. X equals 3.
X equals 3? And it certainly looks like a point where we have a smaller y value than all the points close by. Is that point going to be the location of an absolute minimum as well? Why not?
Because the absolute minimum is at -2.
And we can only have the absolute min occur at one point?
Yeah.
Not necessarily.
Not necessarily.
It's the absolute minimum.
Yeah, but you can have two absolute minimums of the same value.
What?
Look at your absolute max.
So let's go back to one of our everybody's favorite function for a second. Sine of x. Where does this function have an Where does this function have an absolute maximum?
Every time it's, dipping down.
Yeah, I would say at -3 pi over 2, we have an absolute maximum. At pi over 2, we have an absolute maximum. At 5 pi over 2, we have an absolute maximum. Zach, I think you said something that I agree. I think what you said was you can have the same absolute max value occur at multiple points.
Yeah.
And I would agree with that. Mainly because if we look at the definition of absolute maximum, it allows for equality in that at that point A, we need f of a to be greater than or equal to f of x at all points on the graph of our function. There's no reason why that can't occur at multiple points. If this is a strict inequality, then it would have to occur at either 1 point or no points. But you can technically have functions that have an absolute max occur at multiple values of x on the graph if they share the same biggest y value. If you really want to get crazy, you could even have something like sine of x, where technically there's infinitely many points where a function has an absolute max, anywhere where sine of x is equal to 1.
One of the things in the domain of f of x, I get sine of x, but in that domain, the lowest point is -1. So wouldn't there only be one absolute minimum? Oh, yeah.
And for this function, sure.
Okay.
Yeah, I just mean to say in general, you can't say that absolute max or min can only occur at 1 point. In this function, it does for absolute min, but you could theoretically have other functions like sine of x, where the absolute max and or absolute min can occur at multiple points. This one, however, at x equals 3, I would say we have a local min, but not an absolute min. Because at x equals 3, we get a smaller y value than all the points close by. But if we go far enough out to the left, we're going to get points like at x equals -2, where we have even smaller y values. Are we missing any points? Are there any values of x where we have a local max, local min, absolute max, or absolute min still?
We're missing our 2 absolute maxes.
Say what?
We're missing our absolute maxes.
We're missing our absolute maxes. Gadzooks. Where do we have an absolute max on this function?
Negative infinity and infinity.
Holy smokes, at plus or minus infinity? Certainly looks like if we go far enough out to the right, our y values are just going to keep getting bigger forever. And ditto to the left. Should we include plus or minus infinity as points where we could have absolute maxima, do you think? And Josh, you and Zach are really going at it today. I think for this one, I'm actually going to have to agree with Josh.
Oh, I got them last time. That's okay.
You win some, you lose some. And say that for this function, I would actually say f of x has no absolute maximum. Because there's no single value of x, and no x equals infinity and negative infinity don't count as values of x you can plug in. There is no value of x that gives the largest single y value. If you give me something like, oh, Dr. Gerstle, what about at x equals 5 trillion? I would say, well, yeah, but it's 7 trillion, it's bigger. No matter how far out to the right you go, you're never going to reach a highest point, and ditto to the left. So for this function, I would say it has no absolute maximum. It does have an absolute min at x equals -2, but no absolute maximum.
So are you going to say that for any of these values that go to like infinity on each side? They're not going to have any like absolute maxes or minimums if they go down or up. They'd just be non-existent.
Yeah, we could say something like any function that goes down forever on one side and up forever on another side is not going to have any absolute maxima or absolute minima. So something like y equals x, no absolute max, no absolute min, no local max or no local min either for that matter.
Is it true that you have to have endpoints to have an absolute maximum?
Not necessarily. Because if we just took this function, for instance, and flipped it on its head, did something like, I don't know, something like this that doesn't have endpoints to it, we could still say that a function like this has an absolute max at, say, this point here. Later on in this standard, we're going to find the absolute max or min of this function over this specific interval. We'll probably be talking about that in Wednesday's class. But you don't necessarily have to have a function only defined over some finite interval in order to have an absolute max or min. It could happen, it just depends on your function. Let's see, any other questions or comments about this particular function? I think this has it all. We have two local minima, one of which is absolute, one of which isn't. Only one local max, which isn't an absolute max, and turns out we have a function with no absolute maximum on it.
On the quiz, would we get marked down for like putting local max, not absolute max? Or is that not needed, or we can just put local max?
On the quiz, I would probably ask you to specifically say at what values of x does this thing have a local max, and at what values of x does it have an absolute max. And so you'd probably say, oh, it has local max at, replace max with min for this example. You could say, oh, it has local min at x equals -2 and x equals 3. It has an absolute min at x equals -2. And that would probably be how I would want you to indicate your answer. If you don't write something like not absolute min at a point like this, I'm going to assume you're not treating it like one. What's going on with f prime of x at our two local minima? At x equals -2 and at x equals 3. I think f prime is doing something similar at those 2 points. In other words, if I were to draw tangent lines to the function at x equals -2 and at x equals 3, what can we say about the tangent line to the function f of x at those 2 points I just drew out? Mackenzie? Yeah, it looks like we're having horizontal tangent lines at these 2 points, which tells us that f prime at those points is going to be 0. How about our local maximum? What's going on with the derivative there? Looks like our function has a cusp at that point. So Zach, what does that tell us about f prime?
That would be undefined.
Yeah, since we kind of saw back in standard 10, I think, anytime that our function has a cusp like this, or a corner, where the slope from the left is different from the slope on the right, we would say that that function has an undefined derivative. It turns out, and this is going to be our big theorem for today's class, that as long as you have a function that's continuous everywhere, anytime that you have a local max or a local min, it's always going to have one of those 2 types of things occur. That at any time your function has a local max or min, you're either going to have a derivative of 0 or a derivative that is undefined. And this is going to be called, this theorem that's going to tell us this is going to be called the first derivative test. So if y'all want, you can flip the page. I have this written out. So, first derivative test, and this is the only time you're ever going to see me write this out. From now on, I'm going to write this out as the FDT because for sake of laziness. What this says is that if f of x is a continuous function, it's going to say 2 things. It's going to say, first of all, that f of x has to have a local maximum at a point, at say x equals a, if f prime goes from positive to negative at that point, and it's going to have a local minimum at x equals a if f prime of x goes from negative to positive. So let's look at another graph. This one will be a little bit simpler to look at than this big one I drew over here. So here's going to be our function. It's going to behave something like this. So this will be a function, call it f of x. And I'm going to label 3 specific points on the function where something interesting is happening. A, B, and C. If you notice, what's happening to our function at x equals a? What type of point does it look like our function has? What?
Local maximum.
Looks like it has a local maximum. Is that going to be an absolute max?
No, because the graph extends off right in the infinite direction.
Yeah. I think this function would be an example of one, by the way, that has no absolute max and no absolute min, because it goes down forever to the left and up forever to the right if we go far enough out to the right. But this is going to be a point where we have a local maximum. And if you notice, if we look at f prime near that point at x equals a, f prime is going to be positive to the left of x equals a, meaning if we draw out the tangent lines at various points on our graph, they're all going to have positive slopes to the left of x equals a. If we go to the right of x equals a, we're going to have tangent lines that have negative slopes. And so what's going on at x equals a is that f prime goes from positive to negative at that point. The slopes go from having positive tangent lines to the left of a to having negative sloped tangent lines to the right of x equals a. You could also say that similarly at x equals b, we're going to have a local minimum. And if you notice, let's use a different color actually. To the left of x equals b, we're going to have tangent lines with negative slope. So f prime is going to be negative to the left of b. Whereas to the right of b, we're going to have tangent lines with positive slopes. So we could say that f prime goes from negative to positive. What's happening at x equals c?
The graph of f of prime would be like barely touching 0.
Yeah, but specifically to the left and to the right of 0, what can we say about f prime being positive / negative? On both sides?
Yes.
Yeah, I would say that at x equals c, we have a slope of 0. But a little bit to the left of c, we have a positive slope. And a little bit to the right of c, we're going to have a positive slope again. So at x equals c, f prime is going to go from positive to positive again. And at x equals c, we're not going to have a local max or a local min. So if we look at what the first derivative test is telling us, the first derivative test tells us that if f prime goes from positive to negative, like what happened at point A, then we have to have a local max at that point. And similarly, at x equals b, if our derivative f prime goes from being negative to being positive at that point, then we're going to have a local minimum occur. And if it just goes from positive to positive or negative to negative, we're not going to have a local max or a local min. Any questions or comments about what the first derivative test says? So, how are we doing? So, if you notice, as we saw in the last example, at both of the points where the derivative goes from positive to negative or negative to positive, at x equals a, we could say that f prime of a is 0 and f prime of b is undefined. Does not exist because we have another sort of corner going on there. Turns out that first derivative test is going to tell us that the only times that we could have a local max or a local min occur is at one of those two types of points. So in other words, the only points where f of x, where f prime of x, let's say, can possibly change signs, and by change signs, I mean go from positive to negative or vice versa, are at critical points where a critical point is where either f prime of x equals 0 or f prime of x does not exist. So the only place where you could possibly have a local max or min is at a point where the derivative is 0 or undefined. Anywhere else, you can't possibly have a max or a min occurring. So here's a question. Let's see, let's get someone else. Cecilia, I've heard from you guys. We said that if we have a local max or min, then that has to be at one of these two types of critical points. If we have a critical point, does that necessarily mean where f prime is 0 or undefined, does that necessarily mean that we have to have a local max or a local min?
No,
Why not?
I don't know.
Can you think of an example of a function where we have a critical point occurring, but not a local max or min? I think in this function we have a point like that, either a, b, or c. Which of these is going to be a point where we have a derivative of 0, but still no max?
C.
Yeah.
Like, okay, I get what you're saying.
Yeah, sorry to put you on the spot a little bit there. But I think it's possible to have a critical point that's not a local max or min, like at x equals c. If we write that down, we can say it's possible for a crit point to not be a max or min but according to the first derivative test, if you do have a max or min, it has to be at a critical point. So in other words, all local max and local min points are critical points, but not vice versa. Any questions or comments about that? How much time? start. All right, let's look at another example. So on the next page, that's my geometry packet, not this class. We have a function, f of x equals x cubed minus 3 halves x squared minus 6x plus 5. And my question is, how can we find where this function is increasing / decreasing? Where does this function have a local max and or local min? Was that right?
No.
So we have a problem here. What's different about this example from the one a couple pages ago?
There's no graph given to us and an equation.
Gadzooks, I gave you a formula, an equation for our function, but I didn't give you a graph to look at. So we can't just look at the graph and pick off those points. So here's the trick. If you're given a formula for your function and asked to find where does that function have a local max and or a local min, instead of, what we're going to have to do to find those points is to use the first derivative test, or second derivative test when we get to the next standard. And first of all, we're going to find where are our critical points, and then we can check at our critical points, is f prime going from positive to negative, negative to positive, and that can tell us if we have a local max or a local min at those points without ever having to actually graph the function. So our first step, given a situation like this, I think is going to be find the critical points. So in other words, we need to find the points on the graph of our function where f prime is either 0 or does not exist. So what is f prime of x? Emily? Like that? I like it. And I think f prime of x is going to be 3x squared minus 3x minus 6. Are there going to be any points on this function where f prime of x is undefined? Sam?
No, it's because it's a quadratic.
Yeah, it's a quadratic. Or more generally, it's a polynomial. We only have positive powers of x appearing, and functions like that are always going to be defined anywhere you look. So we could say right away, f prime of x is never undefined. So if we want to find critical points, we need to say, where does f prime of x equal 0? So we have a quadratic function, 3x squared minus 3x minus 6 is equal to 0. And we want to find what values of x are going to make that happen. What can we do? Does it?
Pull out a 3.
Okay. That'll give us x squared minus x minus 2. Has to be 0.
And then you can divide by 3 on both sides.
Okay.
Then you FOIL out, or factor out. So x plus 1, x minus 2.
X squared plus x minus 2x will give us a minus x. 1 times negative 2 is negative 2. So what would x have to be in order for this to come out to 0?
-1 or 2.
And we're gonna either get x equals -1 or x equals 2. So it looks like we're gonna have 2 crit points on our function. At -1 and at 7 apparently. Let's say at 2. And according to the first derivative test, these are the only 2 points where we could potentially have a local max or a local min. Is if x equals -1 or if x equals 2. Have a good day, everybody. When we come back on Wednesday, we'll finish this example and look at how can we check to see where does, if this function has a local max or min, or potentially neither at these 2 points. See y'all on Wednesday. I'll let you know if I get the web work issue figured out between now and then.